Okay, so here's a continuation of class 10. This is video 4, and we're talking a little bit about what a Venturi and what a Venturi is. One second, I'm going to pause this video because I have a little carburetor sitting in my sitting over here, so I'm going to go grab it. So one second. Okay, so we could use this Venturi is this. I'm trying to think of the name of. We have a contraction. I'm trying to think of the name of what we say. This is, converging and then diverging. Think of it as a nozzle, right? Converging, then diverging. And as it gets smaller, the static pressure goes down and the dynamic pressure goes up. So when you have a large flow, right here, we can have a vacuum that's generated right in there. And it can be so low that we can cavitate. So we actually have to look out for that. When we go from having a static pressure to a dynamic pressure, we can have cavitation. And if that vacuum gets below the vapor pressure, that's when cavitation, incipient cavitation, begins. We can actually use this Venturi. It's a very useful component to know about, because when the velocity goes up, the pressure goes down. And this is used in something called an air reductor, an air ejector, and carburetors. Now, an air reductor, it can be a very useful thing where you have like maybe compressed air, and you could put it into an air reductor and put the little hose or the little fitting that is attached to right here, and you can suck up liquids in with this. So you could use air as sort of a small pump, if you will, and it's a very effective way to maybe get the prime started on a centrifugal pump. Or you might have seen there's something called electroclean, which is a type of liquid that you can spray, right? We can suck up and we can spray and clean things, and it's like trying to think what we used to use it for on ships, but it was for a variety of things when we wanted to clean things. And I think there's electric clean. I'm trying to remember what we would use it for, but anyway, but you might have like paint guns and that type of thing. They use a Venturi to accomplish that. I think even like spray bottles might even use that type of idea, or like even like in a liquid soap dispenser, maybe something along those lines. Nah, maybe not Venturi, but they're usually like using a positive displacement pump. But anyway, sorry. It's a very useful little component, little concept, this idea of the Venturi. And so that flow restriction creates this vacuum. And amongst the things is a carburetor. So I talked about it in class. I'll bring this in class right here. And so we have a carburetor right here that I got out of this little engine that I use in another class. And just a little quick tour de force of our carburetor. You can see that it has like this diameter is larger than that diameter right there. And what that does is it creates a vacuum, and right in there, I've removed it, but we have like this little jet that we call, right? So now this right here dips down into, trying to get it up. So here's like the jet that's coming out right there. It usually sticks up through the top right in there. And sucking up through here, we have fuel. And this is the bowl right here. This fuel is accumulated down there. And the fuel comes in through here. Right here. Here's the fuel line connected right there. And there's a little valve. There's the shutoff valve. And the fuel will come down through this little hole right here. So there's a passage that comes back down into there. And if you were curious, there's like a little float that's inside the bowl, and the pin goes like right into there, and this thing pivots, right? So when it gets full, the bowl gets full, or the bowl, let's say this the wrong way. When it goes down, right? So the bowl is empty. So it should be opening up this little needle valve, and then when it gets when it gets full, it goes going to go that way. It's supposed to pivot that way. Anyway, here's like a little needle valve that decides when fuel gets put into the bowl. But anyway, it sucks up because of that Venturi action right there. But it also helps to vaporize, right? So it's a low pressure. It goes from the suction right here is allows it to drop, like so when the engine, when you're starting the engine's turning over, it acts as sort of like a vacuum pump, and so that already has a vacuum, but then the Venturi helps to even make the vacuum even less, which turns the liquid gasoline into vapor gasoline, and the carburetor is the thing that helps to mix it. When you start, you usually end up putting the choke on right here, so that really restricts the inlet, and that really helps to increase the vacuum in there. On the other side is the throttle. It's like a little butterfly valve that cycles back and forth, and whatever the spring tension that you put into the little throttle that you have on one of these small little engines will kind of decide what this idle is going to be onto the thing. So anyway, this is a use of a Venturi, very common use, and it's a useful thing to know about. So another application that we had at the Coast Guard Academy that we would use is we had this thing, this lab equipment from Armfield. So let me go, I went to their website. Oh, by the way, okay, so sorry, I meant to show this right here. Here's a schematic that somebody had, and there's what they're calling the jet right in there, where you see the air coming in, and here's like the Venturi, and here's like the little throttle that you see, the little butterfly. So that you can kind of get the idea of, here's what they're calling the bowl right here, and there's like a little float that kind of decides how much fuel gets into the bowl, and then this jet ends up sucking the fuel up there, and you can see that they're showing that the fuel is now getting kind of atomized and turning into a vapor, which is going to mix with the air, and that's going to cause the big kabooms. So at the Coast Guard Academy, we got this what they call a hydraulic bench from Armfield. And one of the cool features, there's a bunch of accessories that you could get with this. It's filled with water, and there's a pump down inside it, and it's got this like a little like segmented area right there with it's got a little stopper. I always thought it's interesting. They like to make the stylized little rubber ball. That's the drain, and you could drain this and then start the pump, and now you could use a stopwatch, and you could time it, because we had you could see the level right in there, right? So you could see the level inside that this little containment area right there. But also, this model apparently has a flow meter available with it. Ours didn't. But we had this accessory, the F128 cavitation demonstration. And so inside this plexiglass little piece was the Venturi. And we had a pressure on the inlet side, and then a pressure in the middle where that's where cavitation might take place, and then there was a pressure on the outlet. So I went ahead and used this piece, and outside of class, we didn't have a lab for that class, but I used this to run a bunch of different tests, right? So here's the volume that I accumulated in the thing, and I had a stopwatch, and I took how much time it took. So that was allow me to get the liters per second, and here it is in cubic meters per second. And for each of these, I use the gauge, and of course the gauge doesn't have very great amount like there. It's tough to really get very accurate on here, but I did my best, and I've watched a lot of gauges in my life. I got kind of better at it with time. But so here's pressure 1, pressure 2, and pressure 3 on these, and yeah, so here's the calculated data right here. But down below, I have the Bernoulli predictions right in there. So I have the flow, right? So that's all these are just this flow from up above. And then so I have the velocity because I know what the area is, right? Because there was 16 millimeter, 4.5 millimeter, and then it goes back to 16 millimeter. Now, truth be told, if this was a perfect Bernoulli thing, the velocity here should equal the velocity there. Well, it has to, but the pressure here should equal the pressure here. But because of losses, it's not going to, right? So you'll notice right here, these pressures right here, some of them are pretty close, but as you go high up in velocity, high up in flow rate, we tend to see that they deviate from each other. So right here is a plot of points 1 to 2, right? So this is the pressure drop between points 1 and 2, and here's for a given flow rate. And this is actually the data that I took. And I did do a demonstration in class where we would get a calculation. So that's that point right there. But here's what Bernoulli is going to pick. We can see the trend matches, even though the actual data doesn't quite match up, right? So there's some deviation. You could say that it could be maybe calibration of the gauges or my inability to read the gauges really accurately. We can also see the pressure. So this is between points 1 and 2, between points 2 and 3. So this is like the recovery. So this is the pressure increase. And you can see that it's pretty close at low velocities, low flow rates, but it gets worse and worse, right? Notably, right here, you could actually witness the cavitation because the thing was made of plexiglass right in there, so you could actually see when it would cavitate. And I don't know if I want to work through I guess I'll work through the problems, not very long. I actually superimpose these back on each other. And we could use this as a flow meter, right? I could say, here's what the static pressure change was. And then I could say, well, here's what from Bernoulli, right here, I'm going to predict and use this as a flow meter to try to say, okay, well, if I observe this pressure change between, let's say, 1 and 2, really, or 2 and 3, either side of it, I could predict the flow, and you could kind of see how that worked out right in there, just using the actual data. So it's kind of an interesting thing. So coming back to here, I can plug in some numbers. All right, so one of the demonstrations I had done in class, I got a pressure 1.5 bar, which by the way is 150 kilopascals. At P1 and at P2, I got negative 88 bar, right? So they're dealing with gauge pressures right there. So, and they're I'm calling this, this is 88 kPa vacuum, if you will. The volume that I chose to use was 6 liters, and it took me 17 seconds to accomplish that. So that's what my flow rate, if I take 6 divided by 17 and multiply it by 0.01, I got 0.000353. And so my velocity, because I know this is 16 millimeters, and up here I got the 16 millimeters. Here's my area for right there. I know that my velocity at 1 is 1.755 meters per second. And then I know that this is 4.5 millimeters. So here is my area right here. So I'm multiplying this right here by 6/17 right there, and this by 6/17. So if we wanted to know what we had. And then I end up with 22.20. So I'm going from this speed to that speed. And then using Bernoulli 1, knowing that Z's cancel out right here, I can predict what my pressure at 2 is going to be from this, right? So I had that 150, and I'm using newtons per meter squared here, and plus 1/2. My density is 999 because it's water, so that's kilograms per cubic meter. And then I have 1.755 squared minus 22.20 squared. I end up with negative 9, I'm going to go 464 right there, e to the minus 3 Newton per meter squared. So that's actually P2 is negative 94.64 kPa compared to my 88, right? So that's like an error of 7.02%, right? That ain't terrible. Especially since it's, we have to remember we were using a gauge. We're using this gauge right here. It's the largest of the three gauges. Let's go back over to there. But that's what we're using. It starts out at 0 right here, and then it goes up to there. So we were near the top of this right there. We're like right in that range, right in there. But you could see that the increments between here. You could even say that some of this might even be the gauge line, right? Because this gauge line, we don't know if that gauge line is leaking, because that's quite a bit of vacuum, right? 1 bar is absolute vacuum, right? Because a bar is approximately 100 kPa, and we know that atmospheric pressure is 101.4 kPa, so negative 101.4 kPa gauge, that's absolute vacuum. So that's a lot of vacuum. So there's a chance there could be like little leaks and that kind of thing. So there's a whole bunch of reasons why they might not be exact. But it was a good demonstration. I wish I had that unit here at UHeart. Maybe if there is a thermofluids lab. I was mentioning this the other day, and it seemed like the mechanical engineers didn't realize that they'd be taking this class coming up. But so here's us right now taking fluid mechanics, and so next semester, all right, you'll want to be taking ME341W, and this is a lab class where you do experiments with fluid mechanics. So even though we don't own this unit right here, I might suggest to Dr. Slaybach that we put that on our list, because I think it's a pretty good thing, because this bench actually you could purchase a bunch of accessories with it. We already have a lot of arm field stuff, so it'll match because it has a nice orange and that kind of thing. So it'll look really cool, wouldn't it? Wouldn't that be nice? So anyway, this was a virtual lab, I guess, sort of, kind of, but not really, because we didn't really do the stuff ourselves. So the end of video 4, we'll have video 5 coming up.